Did you guys do some socket programming since last class?
Yeah.
Reinforce? I know you did malloc. I didn't even have to ask about malloc. But did you follow up that lecture with just a little bit of socket code? Well, you will get there. That much I can promise.
Don't worry, we'll do it later, after malloc, if there's such a life.
There is life after malloc. There is even life after 213.
That's ready, but I don't know if I can.
Okay, the web. No one cares about the history of the web other than old people who live parts of the history of the web. If you care, take a look. Whatever. Web servers. Here's what I want you to think about when you think about web servers. Okay? Remember we talked about the protocol stack. What were the layers of the protocol stack? What was the bottom one? Physical layer. The next one? Link. Next one? Network. Transport. And then? Application. So when you think about the web, right, and you think about HTTP, that HTTP : hypertext transport protocol, where do you think that protocol lives? HTTP is a application level protocol. Okay? In what sense is it a protocol? It defines messages. If I want to get something, I say get, right, and then followed by and then the URL, right? And we'll see that. It defines the messages that are passed between the client and the server. Get me this object. Okay, here it is. Okay? So it's an application layer protocol. So here you see it. Network, transport, application. All right? I know this is also going to shock you, but the web is organized in a client-server paradigm. Yeah. Where your web browser is the client and makes the request to the web server, which sends back a reply. Okay. Web servers return content. They return stuff to the client. We have a slide on this? The stuff can be in all different types. HTML, plain text, PostScript, GIFs, JPEGs, JSON, CSS. Some of the content is static content. Static. It's a vocabulary word. Okay? Static content are things like web pages that are just there on the disk, and it reads them and sends them out the pipe. Read from disk, write to network. Static content. Some of the content is generated in real time by a program. Right? If you go to time.gov and look at the time, right? It's not reading the time off disk, right? It's in some way, shape, or form, right, executing a program that queries the clock and delivers you the current time. That's dynamic content. Static content is delivering things that already exist. Go fetch. Dynamic content is creating things just for you. Does that make you feel special? Time.gov, every time you go, it gets the time just for you. No one else gets that exact answer to that exact query. At least that exact instance of that exact query. Other people make it at the same time, but the one you get was created just for you. Okay. We've all seen URLs, right? HTTP : www.cmu.edu. Right? And then sometimes you see a port number there, like :80 or :443. Unless there's one specified, it's 80. That's the port. 80 is the default port. 443 is the default port if it's using a secure layer. And then the object we want to get. Okay? So if we as a client want to ask the server for something, we tell it what web domain we want to get it from, what port we want to use, and what object we want. That object may be a static object. It may be a dynamic object. We can't tell, right, from our end, whether it's being read from disk or being computed. Right? That name is just a name in an abstract namespace, which is sometimes satisfied by disk and sometimes satisfied by computation. Right? Sometimes static, sometimes dynamic. Yeah?
Why don't we usually use the port number? Like, I go straight to www.cmu.edu, I wouldn't use 80.
Yeah, why don't we usually use the port number? That's the question. The answer is that 80 is assumed if it's HTTP. That's the default. And 443 is assumed if it's HTTPS. That's the default. So you have no reason to use the port number if you're using the default port number, because it can just assume it. If you want, but try, go put the 80 there, you'll see it'll work. Does that make sense? But don't try now. Although that was a good try. Okay. What do we have here? You remember we said we could use Telnet, right? A simple way of shoving characters into a network pipe and getting back characters from a network pipe. We could use Telnet to debug network things, right? One of the things we said last class. Well, here's an example of us using Telnet to connect to a web server. We're telnetting to www.cmu.edu port 80. And we can see that it's done the DNS lookup and it's trying to connect to that IP address, and now it's connected. And now we send the message get /index.shtml space http/1.1. Okay? We're asking for a particular document or a particular object. It looks to me like that's a document, but look, it could be dynamic. We can't really tell. We can't really know. Then we have the host header here, www.cmu.edu. Once upon a time, in a land far, far away, once upon a time, a web server had a name, like www.cmu.edu. You could walk in, and you could find the machine that was www.cmu.edu. Here it is. Okay? And that was exactly what this machine did. Okay? These days, in some cases, we have big websites like www.google.com, and there are a huge number of machines behind that. You can't go anywhere and walk up and say, right here, this is www.google.com. There's no one box you can point at, right? It's also the case that sometimes we have many, many smaller websites hosted by a single computer. Okay? So there's not necessarily a one-to-one mapping. It can be many to one or one to many. And so to help sort of figure this out, when we make a request to a server, we don't assume that it knows its own name, because it may have many. So we tell it the name. I am making a request to get index.shtml from the root of the namespace. And the namespace I'm talking about here is www.cmu.edu. That's the virtual host. Why am I calling it virtual host? Because it may or may not be the name of the physical host. It's mostly just a namespace at this point. Things here are working a little backward compared to how you're probably used to thinking of them. Notice that we have the request or body first, and then we have the header second. Our request body is get/index.shtml. Our request header is host www.cmu.edu. The request comes first, then the header. That's how this application level protocol happens to work. That's how HTTP happens to work. Body first, then header. Then we can see the reply, http:/1.1/200, OK. The date, the time, some details about the server, some details about how we're going to send it, some details about the content type, and then, although we have 3 dots here, it's actually blah! It's firing off all the content that we asked for. Okay? Notice, right, that my header fields are field name : value, whether they're part of the request or part of the reply. Okay? So the HTTP request is a request line, okay? The method, whether it's get, post, options, head, put, delete, or trace, followed by the identifier for the object, followed by the version of the protocol. Okay? Get, traditionally speaking, does exactly what you think it does. It gets an object. In the old days, that meant it would read the object from disk. These days, that means it either reads the object from disk or somehow creates it for us. Static or dynamic, it doesn't matter. Okay? We're asking for some particular thing. And we can even give it some parameters. Post is sort of another way of doing things. It lets us make a request sort of like get, but more importantly, it lets us post or send things with that request. So we post some data, and we get back a response. Okay? Options, head, put, delete, or trace, less common things. Okay? Okay, so the list gets something, post retrieves dynamic content. As it turns out, get can retrieve dynamic content also. Post is named post because it lets you send parameters, basically. It lets you post information and get a response back consistent with what you sent. Options, find out about the server. Head is just like get, but it doesn't actually get the data. Instead, it just gets the header information. This is important for caching. Because if you think you have a copy of the object, you may not want to waste the internet bandwidth to get another copy of the object. That may waste time and bandwidth, right? Instead, you may say, look, just tell me the header information. Okay, the checksums match. We're good. Okay. Put lets you upload a file. Delete lets you delete a file. And trace is used for debugging. HTTP 1.0 was the original version of HTTP. It was basically very simple. You did a get, you got a response, the server hung up on you. You wanted to do it again, you did another get, the server did a response, and it hung up on you again. And there were posts and things like that, but it was very transactional. Make request, get reply, done. Make request, get reply, done. The newer version, 1.1, adds a whole bunch of features. Two important features are that you can make multiple requests from the same connection, and that it supports the named virtual hosts I was talking about. The idea of the web server, one physical web server, can support many hosts. Does things like enables you to send data in chunks, stuff like that. When you get a response, the response line is going to contain a version number, a status code, and a status message. Some common status codes and messages you might have seen are 200, which means OK, no errors. 201, which tells you that something's moved. It provides you with a new URL. Now, you may not have seen a 201. Back in the old days, you did see a 201, right? Browsers would spit out a 201 and a URL and basically tell you, go here. These days, what do you think happens when you see, 301? Redirect. Yeah, your browser just handles it for you. Okay. 403, can't do what you asked me for because you don't have the bits. 404, whatever you're asking me for isn't there. Common headers, content type. Okay? This is important because the content type sometimes controls what happens. If there's a video, right, your browser may want to play it. Right? If it has the right codec for that, if it has the right player for that. If it's an image, it may want to, frame it, right? But it needs to know what it is to do that. It can guess, but this field will tell it for sure. Content length. It's obviously important to know how much you should be reading. Okay. Here's an example where we get a file called test.html, give it the host name. Now this whole stuff here, okay, that's the request header. The request header dumps a ridiculous amount of information about your browser and your environment to the server. Okay, why does it do that? In theory, by telling the server a lot about how you're displaying things, what fonts you have, what browser you're using, what version of the operating system you have. The server can format content just for you. It can know that whether it should give you the mobile version of your website, or the Explorer version of your website, or the Chrome version of your website. Right? It should be able to format things to make it look prettier for you. One interesting side effect of this, of course, is that the details of exactly your operating system and your version number and which fonts you have and blah, 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 tend to be somewhat personal. Not everybody is configured the same way. And so even if you don't identify yourself to a website, they can oftentimes use that to figure out who you are. Because at some point, if you've identified them to your website and you present the same options from the same geographic area at the same time of day, you get the idea. They can quickly narrow in on who you are. I shouldn't say they can often. It's one thing that can be done. Right? It's one way that privacy can be eroded. Even if you don't log in, we can start to make good inferences about who you are. And a big help in this is all the stuff that your browser tells us. Okay, your textbook has an example web server. It's called Tiny. It's a simple sequential web server, meaning it's not multiple threaded. It can handle one connection at a time. It suffers from so-called head-of-line blocking. If one connection is established and sits there and makes request after request after request after request, others have to wait. It can't spawn additional threads. So whoever's at the head of the line getting service, right? It's the old person with a shopping cart full of cat food. You're stuck behind them in line. He's been there. It's only 226 lines of code that is commented, by the way. So it's obviously not a very advanced web server, but it's an excellent example. It accepts a connection from a client. It reads the request. It splits the URI, the identifier for that object. It does something really simple. If the URI contains CGI-bin, it assumes it's dynamic. If it doesn't, it assumes it's static. If the URI does not contain, the identifier does not contain CGI-bin, it looks for it in the file system at the path you specified. That path is not necessarily relative to the root of the file system. It's relative to the root of the web server. The web server's configuration says basically this is where the web server lives. URIs are relative to this point. In the case of Tiny, it's wherever you start Tiny. Okay. If it doesn't contain CGI-bin, it looks for it and tries to serve it to you. If it does contain CGI-bin, it assumes that what you're naming is a program that should be executed. It runs that program and sends you the output of that program. It uses that program to generate dynamic content. Does that make sense? Okay. Ha! Code. Scary. You don't look scared. Okay. So what do we see going on here? So the comment says send response headers to client. Okay, so I'm going to send the headers. Okay, then I'm going to send the body. That's the opposite of the way we saw it on the request, right? The request is the get followed by the body followed by the headers. The reply is the headers followed by the body. So there you see us identifying the server. Normally this would be Apache or IIS or something like that. Instead it's Tiny Web Server, the content length, the content type. Just spit those out. Okay? Notice each time we have a carriage return new line. Right, you see that at the end? Okay. Then once we've done sending the header, we open the file we're supposed to be sending, and we send it out. We memory map the file, giving the file a file descriptor. Giving the file a pointer, and then we write from that pointer. Somebody remind me, what is memory mapping? Have we talked about that yet? Yeah.
Mapping virtual memory.
Bing, we talked about that. We talked about VM, right? Okay. So that's basically we say, okay, here's a file. Let's pretend this is basically memory that's swapped out, and let's just give it a pointer. We take disk and manage it like memory. Make it, so we map that disk into virtual address space. And then once we have the pointer, we just write it. When we're done writing it, we unmap it. Serving dynamic content. The client makes the request. Here we see this request contains the string CGI-bin. So in the simple itsy-bitsy tiny world, that means it's dynamic content. In a real web server, there are much more complicated rules. They look at extensions, directories, so on and so forth. But Tiny just says, hey, it says CGI-bin. It must be executable. Why CGI-bin? Well, bin means binary, like binary program, and CGI stands for Common Gateway Interface. Common Gateway Interface. And that's the standard by which the program and the server interact, so that the server can send parameters to the program, right, execute the program, and the server can collect the results to send them to you. So the request here contains CGI-bin, so itsy-bitsy tiny is going to say, must be a CGI-bin program. Better run it. So the server then forks off a child and ultimately will exec this program, right? But we have to get the output of this program to the server. Okay? So once we fork this off, okay, the output here, right, in some sense goes through the server to the client. Okay. So there are a lot of questions. How does the client pass the program arguments to the server? When you request time from time.gov, right, how does that program know which time zone it should give you that time for? You have to give it the parameters. right? How does the server pass these arguments to the child? How does the server pass other information relevant to the child? How does the server capture the content produced by the child? Ta-da! CGI, the standard. Okay. How does the client pass the arguments to the server? This is the world's simplest example. Notice the URL here and notice the question mark. When we're making a GET request, not a POST request, a GET request, what we do is we encode the parameters into the name of the object. A question mark signifies the end of the object identifier and the beginning of the parameter list. The parameter list is then just field equals value, field equals value, ampersand, field equals value, ampersand, field equals value. Okay? It is an ampersand, delimited list of field equal value pairs. Okay? What if you want to encode something that involves question marks or things like this? Then you have to encode them using their hex values. Spaces are represented by pluses. So if we run this program called adder, we see that number 1, N1, is 15213, and number 2 is 18243. You can tell how old this example is. This class hasn't been 18243 in years. So the results that will be displayed by the program will be 15213 plus 18243 is 33456. Thanks for visiting. There used to be an adder.com. I'm not sure if it's up, but there was adder.com for years. You'd give it numbers and it would add them. It was sort of cool. Computers can compute. Then adder.com went down. It was a crisis in 2013. So Randy Bryant, then Dean, wrote his own adder. And so the adder, we didn't have adder.com, but we had adder, right, at CMU, so we could have the example back. Now, if I'm in a CGI program, how do I actually get those arguments? Okay? The answer is we find them in an environment variable. Remember, there is this string, okay, of variable equals value pairs that any program has access to. It contains things like the search path, right? Stuff like that. Class path for Java. You guys played with this, right? And so we have the environment that contains these things. And so what happens is, after the fork and before the exec, the web server populates the environment with a variable called query string, query underscore string. And it gets, everything there after the question mark. So now if your program wants to know its parameters, it does a get-env to get the environment and asks for the query string. And now it gets this string. It parses the string, and then it knows what's going on. Here we can see it. Get-env, get from the environment the variable called query string. Okay. Now we use scanf, okay, to look for this followed by a decimal, this followed by a decimal, right? This is a really rudimentary parser here. We're assuming things are in exactly the right order, exactly the right way, with no error recovery or anything else. So we look for the string n1 equals, followed by a number, ampersand n2 equals, followed by a number, followed by a new line. And then we take those numbers and we store them into the corresponding variables. Okay. There are a whole bunch of other environment variables that the server offers to the CGI program if it wants it. The server software, the server name, the version of the CGI protocol, the port number, the request method, whether it's get or post, the query string, the remote host, the remote address, the content type, the content length. There are a bunch more. Okay. Yeah?
So wait, this is only relevant for, why is this only relevant for dynamic content?
Well, because if I'm serving a file, the file can't ask and doesn't care what.
Okay, so when we say static, we literally mean like just take that file and give it back.
You got it. Static means take it out of file system, shove out the network pipe.
And all these other things are things we could care about if we were doing dynamic things.
Yeah. Like if I'm trying to generate, if you're running some program, I'm trying to generate content for you, I may care if I should generate a low-res version because it's going on a cell phone, or a high-res version because it's going on a laptop or something, right? I may care about the aspect ratio more likely. Okay. So how does the server capture the content produced by the child? Well, the child's going to produce the content to standard out, right? Because that's what programs generally do. We use dupe2. You remember your friend dupe2 from redirection from the shell? We use dupe2 to redirect the child standard out. So we fork the child, we redirect it standard out, okay, using dupe2, and then we exec it. Okay. So that means the child basically can do what it always does and just write to standard out. Okay. So here we can see we connect between the first pair of dotted lines. We see the request, get, blah, 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 blah. That's the request body, right? Now we see the request header, host colon, right? Request metadata may be a better way of describing that. Then we see the reply. Okay? We see the reply header. Then we see the reply body. Content length, blah, 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 blah. Off we go. Okay? This chunk is generated by the CGI program. The chunk HTTP and server colon is generated by the server. Why is this not generated by the, by the server? Well, the server has no idea what your program is going to do. It's just running it. The server has no idea how big an object your program is going to spit out. It's just running it. Your program generates whatever it generates. Your program knows what type of data it's generating. The server just knows, take it and throw it, right? So here you can see what I was talking about. Fork, set the environment variable, dupe2 the file descriptor, exec the CGI program. Simple as it is. Wait for it to be done. This process I just described to you is the best of the web circa 1998. Okay? These days, the web is much more complex. Right? You go to a web page and the HTML is barely a framework, if that. You download JavaScript and Java programs and things like that, and then maintain a constant connection between the client and the server. So basically what happens is you get the HTML page, suddenly go and grab a whole bunch of Java and JavaScript, whatever else happens to be running Flash, and then those programs running in your browser's environment communicating with the server. So the architecture of the web has become much more advanced. If you care about it, how can you learn?
Class on it.
Which class?
Web applications.
Web apps, yeah. You can spend a semester learning about this stuff, learning about the modern frameworks and how they work. Okay. There's client-side programming, meaning we deliver to your browser a program, and your browser runs that program. That's one thing web programmers do. They run code to run on the client side, right? There's server-side programming. Okay? Programs that run on the server side that generate things to send to the client. Database programming, right? It amazed me when I was doing undergrad advising how many people took web apps but not databases. I can imagine a large number of database applications where you don't have to worry about the web. I can imagine almost nothing worthwhile on the web where there isn't a database somewhere. So I strongly encourage you, if you think of yourself, I want to be a web person. In addition to taking web apps, take databases. It'll make you much better. Much more able to jump into the real world and deal with real sites that almost certainly have databases behind them. Web 1.0 is characterized by, so-called Web 1.0 is characterized by the client making a request, the server setting a response. Request, response, request, response, request, response. Okay? Web 2.0, the client makes a request, the server processes the request, and sends over a bunch of stuff. JavaScript, Flash, Java, that runs over here. That stuff locally generates content on your screen and communicates backward to the server. Okay? And now we see a whole bunch of interaction that's completely programmatically driven. It's not driven by you clicking things. AJAX, asynchronous JavaScript and XML. A collection of client-side technologies that support interactive web applications. The key is asynchronous request to the server to get and store data without having to reload the page. In other words, your page stays there and the programs on it run, updating themselves, updating components. Right? With JavaScript, you can rewrite parts of pages. With things like Flash and Java and things like that, embedded, right? You can control content in parts of those, the parts of those pages they own. The key here is the asynchronous request to the server to get and store data without having to reload the whole page. That basically makes your browser write a GUI that an application can run in, changing whatever part it wants. JSON, JavaScript Object Notation. JSON is a way of encapsulating things to send them. Its main application is AJAX web programming. I mean, that was once true. Now JSON is just a great notation to wrap up simple data structures, to send things. Represents a simple alternative to XML. XML is a I don't want to say complex, because at some level it's very simple, but a notation that allows you to describe very complex things. It has some fairly sophisticated tools for parsing it. JSON is designed just to be simple. Think of it as a way of representing a struct. It's used by a growing number of services for a growing number of reasons. It's a text-based, human-readable format for representing simple data structures and associative arrays. JSON has data types including a number, a string, a boolean, an array, an object, and null. An array is an ordered sequence of values. It's represented the way you'd expect it to, the way you or I would do it, just as a comma-separated list, A, comma, B, comma, C, comma, D. An object isn't really a complex object as you might learn about in some OO class, not in this model. It's just a collection of key value pairs. What's that? What's that? Yeah, it's object-oriented. Right, this is not, at some level it is, but at some level it isn't. It's just a simple thing, basically, where you can have the equivalent of a struct, field and value, and a whole bunch of those. So the field equal value pairs here, right, or the key equal value pairs are not ordered, right? They're just attributes. I can't sort your eye color and your hair color. They're just two properties of you. Okay? I mean, I can, but not in a meaningful way. And null is what you think it is. Here's an example of a JSON. It's great. It's human readable. You can tell exactly what's going on. The properties of this thing are first name, last name, age, address, phone number, enrolled, and previous. There is nothing previous. You can see that's null. You can see if I look at something like address, an address is composed of a city, state, and zip. And then I can see the value of each. And you can see the nesting just uses squigglies. Very natural, right? Very natural. So for our more modern, more-ish modern example, you can see that the JSON here has status and result. Status is 0, success, right? And then the result is 3346. And then a client-side processes the result and renders the result. So we send you a program, right? You make your request, we send you your result, and then your client-side program processes that and renders this however makes sense. Okay, input type, input, length up to 5, ID is n, ID is m. Okay, result is result. Okay, the ID identifies that object. Here's a client-side JavaScript. Okay, what you care about here is that we're getting the values n and m. You see that at the top? I know the syntax is a little foreign to you probably, but it is what it is. Okay? Then you see the AJAX there. Okay? You see us sending the result. Okay? Or pending the result, I should say. So the server loop is going to parse the URL, split it, is going to parse out the URL, log it, process the request, right? And that's what it's going to do. Processing the request. And again, if you take web apps, you'll spend more time on this. You can see if us taking a look at the arguments array, right? You can see us writing the header, and so on. Proxies. Let's talk about proxies. Proxies are going to be very important to you. Proxies will define a large part of your life. In fact, a single proxy, simply known as proxy, will define a large chunk of your life. And yours too. And yours. Okay, because your next project after malloc is to write a proxy. So here's the idea. Right? A proxy is somebody that conducts business on your behalf, right? So in a traditional model, there's the client and there's the server. And the client talks directly to the server. In some cases, it's advantageous to have an intermediary. The client makes a request to the server, but an intermediary catches that request, forwards it to the server, gets the reply from the server, and then forwards the reply. What role might a proxy have? The proxy might simply log traffic to know what's going on. It might filter traffic to make sure that you don't get into things you shouldn't get into while you're at work. Okay? It might be a caching proxy server, such that if you have a proxy on a plane, right, and everybody's checking CNN.com, right, the plane has limited bandwidth. You don't want 1,000 copies of the CNN logo moving onto the plane. Right? Or whatever the video is in the front page. You don't want 1,000 copies of that video moving onto the plane. It'll eat up all the bandwidth. So your proxy may have a cache. So the request goes to the proxy. If it has a new enough version of the cache, it delivers it. If not, it goes to get it. Does that make sense? That's the type of proxy you guys are going to write. A caching proxy. Yeah.
Is there any relationship between proxies and firewalls?
Is there any relationship between proxies and firewalls? So a firewall is a fairly generic name, right, for something that separates and manages network traffic, okay, that implements some policy governing network traffic. And so if I tell you you have a firewall, I don't know at what level of the network or what level or levels of the network that operates. At some level, if it's an application level firewall, you can think of that as a proxy because it's parsing web traffic to determine things and letting some through and not letting others through. It's certainly the case that proxies might or might not be firewalls, but you can think of a firewall as a type of proxy. An application layer firewall is a type of proxy. Okay. Proxies can also be used for so-called transcoding. I forgot that example. Transcoding is the case where the objects are coming from the server rendered for a desktop or something, and you want to strip away the images or downgrade the resolution to make it easier to send over a smaller straw. Back in the day before we had good bandwidth to phones, right, there were plenty of proxy servers that presented the web without images. So you could still read the news even if you couldn't see the pictures. Okay? Anonymization, right? One thing that they definitely can be used for is so you can surf the web and the server can't tell who you are. They know you're somebody behind a proxy, but they don't know who you are behind that proxy. If they wanted to backtrack to you, they have to go to whoever operates the proxy and get logs from them. And maybe the proxy doesn't keep any logs because its goal is to allow anonymity. Yes?
Should that slow and fast be reversed?
Well, we'll get there in a second.
Okay.
But good question. Does that make sense? So the examples: caching, logging, anonymization, filtering, and transcoding. We good there? Okay, so here's an example where we have the clients. That's like our cell phones or our desktop, our proxy server, and the origin server. And this is the internet, and this is some local intranet, enterprise network, the network on the plane, whatever it is. Right. And so what this should be really depends on your model. Generally speaking, locally, you have a wireless access point or an Ethernet cable that's very fast, right? And very cheap. The local network inside CMU going from one end of CMU to another is extremely fast. And it's extremely cheap because it's local. It's not going far, right? The internet is where we end up with slower connectivity because we start to have congestion problems, right? Routing problems, a lot of failure because of scale. So what we'd like to do is deliver something here once and deliver it from here many times, because that saves us the expensive price. Even if we have to pay the cheap price many times, we only have to pay the expensive price once. Does that make sense? Of course, we don't want to be delivering last week's news today just because it's cheap. So we need some way of ensuring freshness, right? And the header information we talked about is going to help us do that. Because sometimes when we get an object, it comes with an expiry date. And we know we can deliver it until then. Sometimes, if this is expensive because we're in a plane, we'll request header information and say, okay, we're past our expiration date, but maybe it's still good. It's like smelling the milk in the refrigerator. Okay? We'll make a request for the header, we'll get the header information, and we'll see the checksum hasn't changed. So now we just update to the new expiry date. We're good to go. There are explicit proxies and transparent proxies. In the case of an explicit proxy, you talk to the proxy instead of talking to the server. You as the client know it's there. Okay? And you make your request to the proxy, and then your proxy does the rest for you. In a so-called transparent proxy, what's happening is there's a device on the network that's parsing the traffic, that recognizes the fact that you're making web requests, that grabs them, filters them, does whatever it's going to do to them, and then sends them on, and does it by processing the network traffic without you seeing it. Explicit proxies, you configure your web browser and say, go to this proxy. Right? Transparent proxies, you have no idea that you're passing through a proxy. The network fabric is doing that. Logging your every web request, and you don't know. I'm sure Snowden thinks you should be scared. Very, very, very scared. Because you know this, the government doesn't know that you look at pornography, and they're going to be shocked when they find it in your stream. Terribly shocked. And despite all of your friends being listed on Facebook, they have no idea who your friends are. They have no idea who on earth you'll talk to, so they're going to have to read your email to figure that out. Well, never mind that. So for more information, the Tiny Proxy server is available. Read the source code. It's great. It's a beautiful example of a client-server network application. Why? Because it's both. It's a server to your web browser, and it's a client to the origin server, to the real web. So you get to see both ends in the same 226-line example. Yay! If you want to see RFCs, the technical specs that talk about things, you can see the RFC for the HTTP protocol. We talked a little bit about the idea of chunk data transfer. The traditional way of transferring is we tell you the size of the object, and we send you the whole thing. That can cause a little bit of indigestion with big traffic. It's nice to know that I need to have a buffer only yay big. And I can take a chunk, deal with it. Take the next chunk, deal with it. Take the next chunk, deal with it. So in chunked mode, we specify the buffer size. I'm going to send it to you in pieces no bigger than this. The last piece may be smaller. Right? And then we're good to go. That solves the problem of how big a buffer do I need to handle this when I don't know what you're sending? Okay? So we prefix each block with the number of bytes, and that tells us how big a buffer we need. You can see that the last chunk has a chunk size of 0, which indicates we're done. So you don't know how many chunks there are. You just keep going until you get a 0-size chunk. Oops. I don't know what I did, but hopefully that'll fix it. Okay. Okay. I think we basically covered this one already. Internet hosts. This shows that basically the number of domain names is increasing. Fast. Shocking. What's interesting to note, according to this question at least, is how many domain names are there and how many IP addresses are there. What percent of IP addresses are associated with domain names? I don't like the question because they have nothing to do with each other. I can have 100 million virtual hosts, right, associated with one IP address. So the question's a little bizarre, right? That's like asking how many people are in cars right now. That's like asking, what percentage of the number of seats, what percentage of the number of cars have people traveling by car right now? That's a really bizarre question, right? Because cars have multiple seats. This is sort of an equally bizarre question because IP addresses can host multiple domain names. And also, domain names can be served by multiple IP addresses. Does that make sense? Any questions? Yeah.
How much of this came out of industry and how much of it came out of academia?
How much of this came out of industry and how much of this came out of academia? The original motivation for the web was researchers sharing information. So that clearly came out of academia. Web, the initial version of the web, before it was commercialized, was clearly driven by academia, by people wanting to share, whose motivation was to share, because that's what academics do, right? But at a certain point, once the commercial interest was clear, right, then it's been driven largely by industry since, if you're asking my impression. Until people were connected to the internet, it didn't matter. Until the internet had people, it wasn't attracting content. And so how that process was bootstrapped was the interesting bit, right? Which was I would say a slow growth, but it was more of an explosion from academia outward. Driven by email and portals and instant messaging. Yeah?
You mentioned using the head request to check if everything is cached properly.
Yeah.
And checking the checksum. How do you know, how can you know that the page is the proper thing? Because presumably multiple pages would map to the same checksum.
How can I know based upon a head request that the page is the proper thing? And you suggested that multiple pages would match to the same checksum.
Unless the checksum is the size of the page.
I certainly don't assume that multiple things would map to the same checksum. A checksum is, although two objects could have the same checksum, it's statistically improbable but possible, right? We consider that to be a type of Byzantine failure, if that would happen. And it would be even more bizarre for two versions of the same object, old and new, to have the same checksum. Because now it's not two completely different objects, right? It's like I've made an edit and I've kept the checksum the same. That's pretty hard. Possible? Yes. Am I willing to squint and say occasionally a program will do a weird thing? Yeah. And that's basically what we do, right? Byzantine errors, at the scale of the internet, Byzantine errors sort of happen, I don't want to say all the time, but all the time. Okay? What happens is something goes weird, somebody says, what's going on, hits refresh. Right? Because there was an error and it was Byzantine corruption, and now the program blows up because it doesn't expect an error, so it has no way of recovering, and so now you hit refresh. And you blame some software bug. Which at some level I'm sure is true. Any other questions? Yeah.
I think there was something about serialization on the JSON slide. Could you elaborate on that?
So serialization is flattening out an object. So if I look at you, you have hair color and eye color and a certain weight and a certain height and a certain gender and blah, blah, blah. These are all attributes of you. They're not ordered. I can't say that I must, there's some natural reason I must describe your eye color before your hair color, or your height before your weight or something. Those are just all attributes of you. They're all equal in that sense. But when I actually try to communicate something, I have to do it in a particular order. I can't communicate to you a whole bunch of attributes in parallel. So the process of taking the attributes of something and ordering them for the purpose of communication is called serialization, communication or storage. And the process of rebuilding a rich object from the serialized properties is called deserialization.
And JSON just does that, essentially orders everything.
Yeah, and JSON is basically a comma-separated list at some level. So it's a serialized version of whatever the object is.
Right, and then so you wouldn't have other data structures other than arrays and things like that? Like if your object had data structures that were like...
So you wouldn't, okay, so the question is, other than the attributes that JSON has, can I have other types of things?
Yeah.
And the answer is only if I can build them with those, by nesting.
Okay, so it'll just nest them. Okay.
And to some extent I can, but to some extent if a property of my object is a callback handler,
Yeah.
that's not going to be representable, right? There aren't permission bits, like, in some sense, on JSONs, right? I can't have, if a property of you is of an object, I shouldn't say you, of some object is an access control list, I really can't communicate that in an enforceable way as part of a JSON. I can serialize the list, but the other side can ignore it. So some things you can communicate, some things you can't. All right, have a great evening, everybody.